two groups here. The first one, Central Texas Consultants Network. We promote the development of members' careers through professional and social networking, including publicizing members' skills and sharing potential professional opportunities, and supports the IEEE Central Texas section. And at the bottom is
Hey,
the
Gene, I'm on a Zoom call. Can you wait an hour?
okay. And for our live member affinity group, IEEE members automatically reach the live member grade when they become 65 years old, and the sum of their age plus IEEE membership is equals to 100 or greater. So you can all do a little math here. I think most people here, I shouldn't say that. A few people here qualifies, I'm sure, or a number of people on this list will qualify. The live members group, we generally host monthly meetings with topics of interest to older members, and they could be either technical or of general interest. And at the bottom here, again, is the link to the website. We invite all of you to help with future meetings, to suggest topics, and even consider to be a member, a speaker yourself. Some possible topics are in the technology area, 5G, 6G, Internet of Things, and AI and smart city. And non-technical topics could be in finance, hobby and travel, and education. And I believe most, if not all of us here are engineers at some point in time, or scientists. So you may have a story that you can tell. So you are invited to give a presentation of that too. What you have done, fun things, exciting things, that technical things that you've done in your career. We would love to hear that. And we could also talk about health and aging, engineering and science history. And I think once a year, we also try to do a tour. For example, this year we had a wildflower. We have a tour to the Wildflower Center in Austin. So it's very varied and interesting. So we invite all of you to be active and contribute here. Also like to Kai, do you want to talk about this one on this future event? We have this live members conference next year.
Actually, you need to point to that page. Right now we're seeing the first page. You want to go to the right page.
You're not seeing the pages as I flip?
No. You need to click that page.
Okay, that is.
Just do it individually. Yeah, okay. You're moving now. Okay. So
can you see it now?
Yeah, I can see it now. Yeah.
Okay, great.
So this kind of announcement for next year, we're going to the inaugural live member conference will be held in Austin from April 14 to 16. April 14 is a Sunday. We tried to pick the week before, but turns out August 8th is the eclipse day. So a lot of people will come in town. The hotel room price went up quite a bit. So we select a very good hotel, Hyatt Regency Hotel. It's right by this Tang River, or what we call Tang Lake, or now it's called Lady Lake, Lady LBJ Lake, yeah, Lady Bird Lake. Sorry about that. So you'll be more information will be available in the September or in all the Alive member magazine and website. So all invited member or any people 55 plus, and also we're locally looking for volunteers. So anybody interested, contact me or Fossey. And for the next few months, for September, we have a local company. We'll talk about REIT-based high performance computing, semiconductor chip and system. So Doug Norton will be talking on that topic. And October, we'll have a gentleman, Scott Collins. He's running the Austin Bio Council. So we're going to talk about some biotech topic. And November, normally we have a group lunch. We're going to have a barbecue this year in the county line by the hill. Anybody, David, you like barbecue, you can come join us. Yeah, that's the announcement. And maybe you want to also, we are a number of co-hosts, like co-hosts from Fort Worth, Denver, and Oklahoma City, and Galveston Bay. So we have 4 co-hosts, live member group here for tonight. So Lewis, please go to the next page so that Clyde can do the intro of the speaker. Okay, got it.
All right. Can you hear me all right?
Yes.
Okay. Speaker tonight is Lewis Thompson, and the topic is Introduction to Solar Weather. I have heard Lou speak on many occasions to the Austin Amateur Radio Club, and his talk on the solar weather and propagation conditions is always a highlight of that meeting, and he does that every month for the club. He's a senior engineering scientist at ARL, UT's research laboratory. So a registered professional engineer in Texas. Also a member of the Sigma Chi Society and the Honor Society for Science and Engineering. Many illustrious people belong to that. Is right in there with Einstein and others.
Wow.
And also was responsible for the design and building of the ionosphere, which I am sure that we will hear a good bit about in the talk that follows. And I wasn't even aware that it was here until listening to Lou's talks, and now I consult it on a pretty regular basis. He's currently the vice president of the Austin Amateur Radio Club, and he used to be the former president. And so he's been very active in the club for many years. He's also the current liaison to the Texas Military Forces for Region 6 Army Mars, and also teaches classes to the Texas Military Forces, our local Texas forces, and in high frequency radio propagation antenna theory. This is a short list. He has worked on many other things, and so as opposed to turning this into a complete resume, I think this is an indication that Lou is very well informed about this topic, and I'm looking forward to his talk. So we might put the next page up if you can, Luis. Yeah, and probably the most important bullet here is the first one, which is please mute your audio unless you are going to have a question or participate in some way, because a lot of times we end up with crosstalk, especially with, looks like we have about 23 members online right now. So it gets kind of confusing if you have your audio on. So if you'd mute that, that would be really, really helpful. And put questions in the chat box, and be sure to turn your both your audio and video on, or at least your audio on if you want to ask a verbal question. Okay, with that, I'll turn it over to Lou.
Yeah, Louis, please unshare, then I'll turn on mine. All right, so. All right, so you have this. Oh, I need to kind of. Do you see full screen or half a screen?
I see a half a screen.
Half.
Okay, let me flip the.
Partial.
Yeah, I'm using a TV screen as my. I think there's some way I can flip the screen.
So this is similar to what I had earlier, I guess.
Yeah, right. Okay.
Well, it's usable like this. It's just not going to be a full screen.
Yeah.
Can you go to
Get a Macintosh?
Can you go to presentation mode?
Yeah,
like
I did
slide
already in presentation mode.
already in?
Yeah,
Oh.
yeah.
So
Okay, so I think this is
looks like a problem with Zoom.
no, it's Zoom or the other. Let's see. No, that's a whole page. Okay, maybe here.
Right, change your view up in the upper right corner to standard. Try that.
Okay. I think there's some selection. High presenter view. Oh. So this is stand-up.
Yeah, that's okay.
That's a little bit larger. It's a little bit better to see.
Yeah. Okay.
Yeah.
Okay. So let's go with that then.
Okay. Well, I'll go ahead and get started. Welcome to everybody. This discussion. Okay. We'll just stay on. We can stay right there.
Okay.
This discussion is going to be on HF propagation, which you may not have a background on, but I'm going to try to provide that. HF radio is very popular at the moment with the military. DOD has directed all of the services to develop HF again because of the threat to satellite and internet communications. And so this is a subject that is not old-fashioned or obsolete. I will first of all talk about ionospheric propagation, which will include near vertical incidence skywave, NVIS, long range, selecting the correct frequencies for both NVIS and long range, and some propagation modeling. I will then shift to discussing the effect of solar weather on ionospheric propagation. Next slide. Okay, HF propagation is basically from 3 to 30 megahertz. There are 3 different modes of HF propagation: free space, where you have no boundaries, and sort of like two spaceships talking to each other with no reflecting boundaries. Ground wave propagation, where the electromagnetic wave is regenerated in the conductivity of the Earth, and basically it follows the Earth's curvature. Losses are very high in the 3 to 30 megahertz band, and this is mainly used below 3 megahertz for AM radio. And then finally, the only propagation mode that is
You're in a meeting, right?
It's being recorded. I watch it. Like,
whatever one, please mute your.
looks like I'm in there.
Thank you. And finally, ionospheric skip, which is the only propagation mode that is affected by solar weather. It's basically long distance and near vertical incidence skywave propagation, the 2 modes for ionospheric skip. Next slide. Next slide, please.
Okay.
I don't know whether you can click on that and make that active or not.
Yeah.
Well, maybe it's not going to work. Okay. Well, anyway, what this shows is that the ground wave propagation for the sky wave, the ground wave propagation is relatively short. Then you have a long distance sky wave where there is a skip zone, and this skip zone is a function of both the condition of the characteristics of the ionosphere and the frequency you have selected. So
Hey,
you will
Kai,
have.
Just Lou, Kai, you're
Yes.
not you're not projecting that on screen. You're just looking at the file. Click on the little screen down there on the bottom, and that
Yeah,
makes
I tried that. We get the wrong things.
There you go. Okay, now you're there. Okay.
Okay, good. Thank you, James.
Yeah.
No
Okay.
charge.
Now go to
Okay.
the next slide. I'm sorry. Go to the
Okay.
next slide.
Okay.
Next slide.
Okay.
Now it's working.
Okay. All right. All right.
Okay. Okay. You can see the ground wave propagation. You can see the sky wave propagation. And again, the skip zone is a function of the condition of the ionosphere and the frequency you have selected. And so, as you can see, there is a zone, exclusion zone, that can be generated for this type of propagation. Next slide. You can eliminate the skip zone by going to near vertical incidence sky wave propagation. This is a special mode where, by selecting the frequency and the type of antenna you use, you can eliminate the skip zone. It's very popular with the military and emergency amateur communications because it allows communications, you might say, out to about 500-mile radius around the stations of interest. And most interestingly, with respect to the military, if an enemy station attempts to DF you, direction find you, it appears that you're coming from the sky unless they are very close to your transmitter. So it's relatively secure. Next slide. So let's talk about the ionosphere. It consists of layers, the F2, the F1E, and D layers. Let's see what those layers really amount to. Next slide. So this is a rather complicated slide that talks about the ionospheric structure. Note that the horizontal axis is the electron density in cubic centimeters. So the ionosphere is really a structure of different densities of electrons. The ionosphere is created by the use of gravity, or you might say the absence of it, and solar radiation. So as you go up in altitude, gravity is reduced, the atmosphere gets thinner and thinner. When you get to about 350 kilometers, the atmosphere is so thin that the monoatomic oxygen molecules that are ionized by solar radiation cannot find their the electron and the ion cannot recombine in any kind of reasonable time. And so you have a layer that's even present all night when the sun isn't shining. So it's a very thin layer. Well, how thin is that F2 layer? Well, at 350 to 400 kilometers, the International Space Station is orbiting, and you can see a picture of it to the right. The International Space Station does have to expend fuel occasionally to maintain its orbit, but in general, the atmosphere is very thin. As you go down into the atmosphere farther, it takes higher energy solar radiation to ionize the particles in the F1 and the E layer. The other important layer is the D layer, and it is ionized only by hard X-rays and Lyman alpha radiation. This layer does not reflect radio waves, it only attenuates them, and I will talk more about that later. Next slide. So let's talk about the typical long-range propagation first. If you have an antenna that's directing all the energy at a very low angle, you can get out the optimum for the 200-mile or 320-kilometer F2 layer. You can get out to about 1,800 miles or 3,000 kilometers. This is maximum for one bounce, but these long-range bounces can be complicated because sometimes other layers like the E layer can be involved. And I'll give you an example of this kind of propagation. Next slide. This is a very interesting, unusual propagation mode called transequatorial propagation, or TEP. It was discovered by amateur radio operators years ago. Basically, you have a station on either side of the geomagnetic equator. Near the equator, there's highly ionized areas of the ionosphere. And so the radio wave, instead of bouncing off the ionosphere, hitting the ground and bouncing off the ionosphere again to make this hop, or a two-hop propagation, it simply is bent by the highly ionized regions, goes across the geomagnetic equator, where it's bent back down to the second station with much lower propagation losses. So this is just an example of how complicated high frequency long range propagation can be. Next slide. So let's get back to near vertical incident skywave propagation. It's good out for about 500 miles. Note that you have to have a special antenna that puts all the energy straight up within a plus or minus 50-degree cone. A lot of amateurs will call this a cloud warmer, but it's doing exactly what it needs to do to provide emergency communications or military tactical communications out to a radius of 500 miles. Next slide. So let's define some terms. For NVIS to operate, you must operate below the local critical frequency, and notice that is capital. The critical frequency is the frequency above which your radio wave is going to go straight on through the ionosphere, never to return. Notice that we're not going to worry about the critical frequency of the E layer. This is on the F2 layer. Next slide. So the critical frequency increases with increased ionization of the F layer. More electrons in the F layer increases the critical frequency. Certainly, the increase in ionization will happen during the time of day. Noon you'll have the highest ionization because the sun is overhead. Time of the year, you would think that summertime would be best, but it turns out that terrestrial heating will cause the ionosphere to heat a little bit more and expand slightly. So the winter actually has the best critical frequency at noontime. And also the time of the 11-year sunspot cycle. More sunspots seem to produce more ultraviolet radiation. Not well understood, but that is the fact. Next slide. So let's talk about maximum usable frequency. Notice that the maximum usable frequency for any circuit is simply that critical frequency, which we've already talked about, divided by the cosine of the angle from the takeoff beam to vertical, and it's graphically shown below. Note that if you know the height of the ionosphere, which is going to be measured by an ionoson, and you know what the critical frequency halfway between you and your recipient, you can calculate the maximum usable frequency for that circuit. And you're not using any kind of estimates. This is an actual measurement that an ionoson will measure at that midpoint if there's one available. Next slide. So how does the critical frequency vary with the sunspot cycle? This is a little bit old data, but it's certainly valid. This is during the peak of sunspot cycle 23, but it's exactly what happened for 24 and is now happening for cycle 25. Note the critical frequency, and the horizontal axis is the local time in Central Standard Time. The vertical axis is the critical frequency. As the sun starts coming up around 6 to 7 a.m., notice the critical frequency rises up to about 9.5 megahertz. And then as the sun starts to go down in the afternoon, the critical frequency drops, takes a dip, and then returns to the 4 megahertz evening critical frequency. Next slide. In contrast, during between cycles 23 and 24, and between 24 and 25, you see the critical frequency about 3 megahertz, and it barely rises to 4.5 to 5 megahertz during the day, and then falls back off to 3 megahertz in the evening. Next slide. So why don't we just operate at a low frequency all the time and not have to worry about what the critical frequency is? D layer is going to prevent that. Remember that the D layer is down at about 80 kilometers. It's ionized by hard X-rays and Lyman alpha radiation. It's dense enough that as soon as the X-rays go away, the D layer ions and electrons will recombine. So it's a rapidly changing layer, and we'll see how that can hurt us in the future. But right now we have to worry about just what the D layer is going to do to us. Next slide. So when our radio wave is trying to get to the F2 layer to propagate, either for NVIS propagation or for long-range propagation, note that the radio wave has to pass through the D layer twice, and each of those passes, there's some absorption. So that controls the lowest usable frequency. As we go down in frequency, the absorption will increase. It's a daytime effect. And there's also an interesting phenomena called gray line propagation, where right at dusk, the sun is shining on the F2 layer, keeping it ionized, but the sun is no longer sending X-ray radiation to the D layer, resulting in the D layer disappearing and having excellent propagation during this period of time. Since it's an absorption phenomena, it's a function of transmit power and mode of operation. More transmit power or a narrower bandwidth signal can increase your range or your operating capability. Now, most importantly, this absorption is a function of 1 over the frequency squared. So trying to operate as close as you can to your circuit maximum usable frequency is what you want to do to maximize the signal that you have available for your circuit. Next slide. So this is just trying to encourage amateur radio operators to start learning how to use an ionoson and read ionograms. Next slide. Okay, the ionosons are really the only way you have to actually measure the propagation properties of the ionosphere in real time, besides actually trying to make a contact. We call that a radio check in the military. So the ionoson is an instrument, a scientific instrument that effectively measures the electron density and defines the layers, but it also tells you exactly what the critical frequency is, and I'll show you how we do that. So let me describe the ionoson. It's basically an HF radar. It has a large transmitter. It sends signals to the ionosphere, and then they're reflected back and received. The transmitter antenna is shown in the upper right. It's a monster. It's 2 80-foot towers, 180 feet apart. That is a large delta loop. It has a terminating resistor in the top of it so as to keep its standing wave ratio compatible with the amplifier. It's driven by a 4,000 watt peak envelope power amplifier. The signals are received on 7 different 20-foot tall receiving antennas in a Mills cross, north, south, east, west, and those signals are processed in the electronics. Next slide. So there's a large number of ionosons active all over the world. The reason for this is both scientific. The scientific community continues to try to model the effects and the performance of the ionoson. It's very difficult because we're basically dealing with the function of a plasma in a weak magnetic field. And I think the scientists trying to develop fusion power are running into the same mathematical problems. Next slide. So ionoson data are available at the DID base website, which can be found on the on the Region 6 Army Mars website. You click on menu and then solar weather. I'll give you that URL later. And then under DID base is a complete listing of all of the world's ionosons, and they're categorized by year, month, day, and time. And I'll talk about the other information that's on this Region 6 Army Mars website. Next slide. So let's talk about how an ionogram is read, and actually this tells us how the ionoson actually works. So the bottom axis is the transmit frequency of the ionoson in megahertz, and the vertical axis is the echo range in kilometers. So these ionoson starts out at about 2 megahertz, and it steps through to 20 megahertz in 100 kilohertz steps. It transmits 64 total pulses at each frequency. 32 pulses are transmitted to the receiving array with a left-hand circularly polarized configuration. The antennas rapidly switch to a right-hand circularly polarized, and the second 32 pulses are sent. This allows the 2 different waves that are actually returned by the ionoson, by the ionosphere, to be received. When you send a plane wave to the ionosphere, you do not get a plane wave back. You get a regenerated pair of waves that are elliptically polarized and 90 degrees out of phase. One is called the ordinary wave, which is the red plot, and the other is the green, which is the extraordinary wave. As you can see, the red plot with its echo disappears at the there's no echo return beyond 8.8 megahertz. That is the critical frequency measured at this day and time by this ionoson. Note that the true height of the F2 layer is slightly different from the actual echo, and this is because the software measures the velocity of the density of the electrons in the ionosphere, and then adjusts the velocity. Since the velocity is no longer the speed of light within the plasma, it adjusts the velocity so as to get the true height versus density. This is the H sub m F2. And you'll note that the FOF2 at the top, which is the frequency of the ordinary wave off the F2 layer, is 8.8 megahertz. At the bottom is another important table called the oblique propagation MUF chart. The D is the skip distance in kilometers, and the MUF is the frequency for that skip distance. So, for example, if you could handle a 400 kilometer exclusion zone or skip zone around your station, you could operate at 10 megahertz rather than 8.8 megahertz. With the 1 over f squared deabsorption phenomena, you can get considerably better performance by moving up in frequency as long as the circuit can operate at the maximum usable frequency. Next slide. So let's look at the Austin ionosphere 2 days ago. This is at 8:35 a.m. local time, Central Daylight Time. This plot is available every 5 minutes. Note that the critical frequency was 8.5 megahertz. The height of the ionosphere was 254.7 kilometers. And at the bottom, the longest skip distance available, 3,000 kilometers, can be achieved with a 28.3 megahertz frequency. So in the ham band, the 10 meter 28 megahertz ham band would be available for skip communications at this time of day, if that's the ionosphere data halfway between you and who you wish to talk to. Next slide. So another interesting plot that we get from NOAA. NOAA receives all the ionosphere data and then resend, and then this is available for consumption, and it's basically called the trending chart. The horizontal axis is the time of day, UTC, and the vertical axis is the critical frequency. Blue is today, red is yesterday, and green is the last 5 days. The extra noise in the green data is caused by a problem that we are solving with the ionosphere right now. It had some receiving problems during high deabsorption periods. So this could be very useful to anyone trying to do emergency communications. You plot this out, and unless there are other extenuating factors, what happened yesterday is going to happen tomorrow and the next day. So it's very useful. Note that as the sun starts to go down around 0100 Zulu, which is like 7 to 8 p.m., the critical frequency starts dropping. It settles out at about 6 megahertz, then it's going to drop to about 5 early in the morning before the sun starts to come up around 12 to 1300 Zulu, and the critical frequency rapidly rises as the ionosphere gets new ionization from the ultraviolet rays of the sun. Next slide. So an interesting phenomena, which is still not well understood, is called sporadic E propagation. It's one of those factors that the ionospheres cannot deal with. Sporadic E typically happens in the late June and into the summer time, and also a little bit of sporadic E in the middle of the winter. It is a very narrow, highly reflective layer in the E layer, about 110 kilometers, and it has the ability to completely reflect radio waves. Even the 4,000 watts from the ionosphere will not punch through under some circumstances. But you could still conduct regular skip communications. You're just skipping at half the distance, half the height you normally would. Note that the maximum usable frequency can be much higher, 25 to 150 megahertz versus the typical 10 megahertz critical frequency, and maybe an MUF of 30 megahertz under ideal conditions. So let's talk more about that. Next slide. Well, the hint to detect what's called blanketing sporadic E, which is where signals can't get through, is that you see a funny performance on the trending chart, the critical frequency chart. You can see the spiking in the middle of the night, and in the afternoon, the ionosphere cannot change its critical frequency that rapidly, so something is wrong. And the only way to discover what's going on is to look at the actual ionogram, which is shown on the next slide. As you can see, the F2 critical frequency curve is completely gone. all of the energy from the ionosphere is being reflected by the first sporadic E layer, and then you simply see repeat echoes as the signal hits the ground, goes back and hits the ionosphere, the sporadic E layer, and goes back and is received. So you see these multiple layers at 110 kilometer spacing. The tables to the left and the bottom tables have no validity, but you can still operate perfectly okay. We've operated many Mars and amateur nets out to 8 to 10 megahertz, as shown by this ionosphere data. What you have to be careful of if you're doing this is that the sporadic E layer can disappear. And if it does, if you're up at 8 or 9 megahertz and your critical frequency is 5 or 6, you could be your net could immediately fail. So you have to take into account what you think the critical frequency or your MUF is going to be for the net and stay on that frequency. Next slide. Most interestingly, this is the return of the F2 layer that I just showed you. The layer faded out just enough that the ionosphere could punch through it, and note what an excellent job that software did in curve fitting to the actual F2 layer reflection, the red reflection, and got the correct answer of 4.1 megahertz. I'm always amazed at this slide that it does such a good job. A lot of the work we do in the Mars program and in the amateur community is digital now. So you can imagine the intersymbol interference trying to reflect a signal off of an ionosphere that looks like this. So, but it does seem to work. It's amazing. You just have to pick your characteristics of your digital signal, and you can actually work under these circumstances. Next, yes.
Go back to the previous slide.
Yeah, back to the previous slide. Okay.
Yeah, okay. And there's all kinds of little red and green dots way out to the right under repeated echoes, a label, and some high in the middle. What do you make of that? Are those just outliers or bad data or what?
I think it's just noise. Just the tiny little spikes. Well, see, you can see the sporadic E repeat echoes, and then you see echoes for the F2 layer return to the left. Those are just repeat echoes.
Okay, so it's noise. All right, thanks.
Yeah, it's not noise. It's the signal hitting the ground, going up, hitting the ionosphere again, or the sporadic E layer, being identified and plotted, and that just goes on with repeated echoes. But the software, the Artist 4.5, does a good job of identifying the initial F2 layer return and reporting that correctly. So it's a very complicated problem.
Right, sure.
Okay, good. Thank you. Next slide. Okay, this is kind of a joke. As some of you know that are amateur radio operators, there is a amateur radio ARRL field day last week in June every year. And so for tens of thousands of amateurs get into the field, set up emergency antennas, operate on emergency power from Saturday at noon till Sunday at noon. It's called field day. And so Saturday night, all the hams are barbecuing food for that Saturday evening meal. So we've all decided that since no one seems to know what causing sporadic E, that it must be all of that barbecue fumes going up and improving sporadic E propagation. So a little joke that the amateurs like to see. Next slide. So propagation prediction. The rule of thumb for critical frequency, as you've seen, is somewhere between 2 and 4 megahertz at night and 4 and 8 megahertz daytime. Well, that isn't anywhere near sufficient because the critical frequency filter is very, very tight. If you're off by more than a few hundred kilohertz, you may not have a communications circuit. So you must use ionosondes or radio checks to be able to determine the correct critical frequency in order to be successful with any types of prediction, military or emergency nets. Propagation prediction programs. I like HF. I like VOACAP. The other program I've been using is no longer available. There are other programs, but VOACAP is considered by myself and the military to be about the best program for propagation prediction. It works quite reasonably well for long-range propagation, but for NVIS, it does not work. Web information is the Region 6 Army Mars solar weather page. And part of that is the DID base as shown here. And then interestingly, there is a series of international beacons located all over the world. They are omnidirectional, deep GPS time-based beacons. They transmit at 100 watts, 10 watts, 1 watt, and 0.1 watts from 14 megahertz to 28 megahertz in the amateur band. And I have been able to hear many of those beacons halfway around the world at 0.1 watts. It's just amazing. A very good program for you that are interested is the program called Pharos, and it costs a little money, but not very expensive. It will automatically control your transceiver, changing the frequencies, and has a very good data analysis program built into it that will help you monitor 24/7 the propagation of these beacons to your location. Next slide. So now that we've talked about what ionospheric propagation is, let's talk about how solar weather affects ionospheric propagation. We'll talk about the parameters like solar flux and sunspot number, the Earth's geomagnetic field, solar flares, proton events, and finally coronal mass ejections and coronal holes. Next slide. So sunspot activity 2 days ago. This is a magnetogram that uses the Zeeman effect to measure the polarity of the magnetic fields on the sun. When two magnetic fields get very close together, that produces a sunspot. And you can see sunspots numbered on this magnetogram. If the intensity difference between the magnetic fields close together gets high enough, that can produce a solar flare, kind of like an arc over if it were voltage, but instead it's magnetic fields. Next slide. So we have to have, what's always amazing to me is that we have no real way to measure the true ionization intensity of the ultraviolet rays from the sun. So two different secondary indicators are being used. A very old one is the sunspot number, or the Wolf-Zurich sunspot number. This is a special count of the number of visible sunspots. The sunspot number varies from 0 to 200. It follows an 11-year sunspot cycle. It turns out that the 12-month running average produces the best fit with propagation conditions, and increased sunspot number leads to higher MUF, which of course means there's more ultraviolet radiation. Solar flux is the other way to measure the intensity of the UV radiation. It's a measure of solar radio noise from the sun at 2800 megahertz. It varies from 50 to 300. Increased solar flux leads to higher maximum usable frequencies. It follows 11-year sunspot cycle. And interestingly, it does not exactly track propagation conditions. When the solar flux index rises suddenly, it takes a few days before the actual increase in critical frequency is seen. Next slide. So this is just shows you how the two are related. On the left is the sunspot number, and on the right is a year of solar flux. It turns out the two are related by a second order polynomial, as seen in the center block. Next slide. So I'm not going to go into a lot of detail. This will be available on the PDF that I have supplied to the group for publishing. It's just the rules for how you do a sunspot count. It's still counted by human beings, and one of their plots is seen on the next slide. So that's complicated, requires a lot of training and care to be accurate. Next slide. So the sunspot number is shown. The red plot is what the leading scientists predicted for number 25, solar 25. And as you can see, the performance is much better than has been predicted. All of us are hoping that this will continue for the next few years. Next slide. So solar flux measurements, I'm not going to read this to you. I'll let you read it. It's basically an attempt to understand the emissions at 2800 megahertz or 10.7 centimeter wavelength source from the sun, and how this relates directly to the intensity of the ultraviolet radiation that would be ionizing the ionosphere of the Earth. There are two instruments, both located in Canada, that make this measurement 3 times a day. They're averaged and then delivered each day. Next slide. This is just a picture of the one of the two flux monitoring stations of Dominion Radio Astrophysical Observatory in British Columbia, Canada. Next slide. So the solar flux, just like the sunspot number, is rising since they're related. And you can see that the performance of cycle 25 is doing much better than it was forecast to do. Next slide. So this is just a very busy plot that shows you the fluctuation of the sunspot number and the solar flux with respect to a year of plotted data. You can see there's been some very extreme high peaks, and we're still holding out at a very high level. Next slide. So another indicator that we have to measure and take into account for HF propagation is the fluctuations of the Earth's geomagnetic field. When the Earth's geomagnetic field fluctuates, it induces current, electric current, into the F2 layer, which is a plasma. As you know, a plasma is conducting. So this additional fluctuation will cause the F2 layer to heat and expand, which lowers its critical frequency. We have to have a way to measure this. And of course, increased geomagnetic activity means a lower critical frequency. So we have the planetary K index. This is a pseudo logarithmic scale from 0 to 9. It is the average of 13 mid-latitude located magnetic observatories. I'll just show you a list of those for your information in a few minutes. And it's each of those stations variance from a very quiet condition. 0 to 1, and then those 13 stations are averaged over a 3-hour average, and that produces a planetary K index for that period. 0 to 1 is quiet conditions, 2 to 4, some degradation, 5 to 6, minor storm, and 6 to 9, major storm conditions leading to HF blackouts. The planetary A index is simply the average of 4 planetary K indexes, but they take the pseudo logarithmic numbers, convert them to linear numbers, and it goes from 0 to 400. It is effectively yesterday's magnetic field variance. Next slide. This is just a list for your information of the 13 observatories used to compute the planetary K index. Next slide. This is a map. The red stars are the planetary K index geomagnetic observatories, and you see they vary from New Zealand to Australia, across Europe and the United States. The blue stars are disturbance storm time observatories near the equator, and I'll tell you more about those in just a moment. Next slide. So our planetary K index for the last 3 days has been very quiet, no higher than 2, maybe 2.5. And so it's a very quiet geomagnetic period. Next slide. So another measure of the geomagnetic storm conditions is called the disturbance storm time. I don't know how they came up with that name, but it is a measure of the equatorial current, the equator current, which increases as the Earth's geomagnetic field fluctuates more and more. It seems to be the best indicator of storm severity. The DST is expressed in nanoteslas, and it's measured in 4 nearly equatorial geomagnetic observatories. The DST will show a rapid negative increase, which is an indicator of how bad storm conditions are going to be. When the DST is high, the Earth's absolute geomagnetic field will actually be reduced in intensity. Next slide. So this is just simply showing the ring current, the equatorial ring current for the DST measure. Next slide. So geomagnetic conditions for 15 August, Bravo Zulu is 2 nanotesla. When that number is negative, it means that we're having a minor magnetic storm, if not serious. The speed of the solar wind is 291 kilometers per second. 360 is nominal, but can be as high as 900 kilometers per second. The density is 2.54, but typically will be around 5 to 10 protons per cubic centimeter. This comes from the NOAA Discovery satellite, which is in an L1 Lagrange point orbit. Here's the disturbance storm time that I just talked to you about. It's -12 as of the 15th. Notice that I put an arrow at a DST that was about -120, and this came from a coronal mass ejection impact from a 5 August X 1.6 solar flare, and I will give you more definition of that in a minute. The GOES satellite in geosynchronous orbit does more than take weather pictures. It also measures protons, electrons, and is a good magnetometer. So this is the sinusoidal fluctuation of the GOES magnetometer. I think it's a GOES 16. Next slide. So a good source of solar weather is solarhams.org. This is their forecast for 15 August. The solar flux index is 154. The sunspot number is 85. The panel below that shows that the planetary K index is going to be between 2 and 4 for the next 3 days through the 17th. The right panel shows the solar flux X-ray. We'll talk more about that in a minute. as well as the global D layer absorption. And then the current solar flare threat is given for C, M, and X flares. This comes straight from NOAA. And then the number of visible sunspots are shown below with their category. Next slide. So let's talk about solar effects on propagation now that we have some definitions. As we've discussed, ultraviolet radiation from the sun is good. It ionizes the layers until it actually ionizes the D layer, but that's only under extreme conditions. X-ray radiation from solar flares is bad. Proton events can be bad. Coronal mass ejections bad, and coronal holes are bad. Let's look at each one of these and how they affect propagation. Next slide. So when a solar flare occurs, that's when the magnetic fields arc over, it produces X-rays. X-rays, of course, are an electromagnetic wave. They travel to the Earth at the speed of light, takes about 8 minutes to arrive. As soon as we see the flash, the blackout is already started. This occurs for an M or an X class solar flare, a certain intensity of X-rays. Those X-rays are going to penetrate down to the D layer and ionize the D layer. If the flare is directly overhead, we're going to experience a sudden ionospheric disturbance, which simply means that it's going to black out radio communications for a short period of time. It is a daytime effect because the X-rays can't go through the Earth. And the first time an amateur experiences a sudden ionospheric disturbance, just all of a sudden, the band goes from lots of people talking, everything going on, and all of a sudden the circuit is completely dead. You hear nothing. Your first indication or inclination is to go outside and see if your antenna has fallen down. It's that sudden. Next slide. So what's happening is the intense X-rays are penetrating down to the D layer. They're hard X-rays, and they're going to cause the D layer to ionize, which is going to increase absorption dramatically all of a sudden. But since this layer is at a very low altitude, the ions and electrons will recombine very rapidly as soon as the X-ray excitation goes away. Next slide. So we already talked a little bit about this. You can see that on the way from your transmitter to the F2 layer, you have to pass through the D layer, where part of your signal is absorbed, or all of it. And then the same thing happens on the way down to your receiving station, and the same thing happens for long range as short range. Again, it's a daylight effect. The absorption is a function of 1 over the frequency squared, and you can compensate by increasing your power and your back just a little bit. One more.
Okay.
One more.
Okay. Oh.
I don't know where we back up one.
Okay.
Well, let's just stay right there. Okay. Yeah. Okay. Here's the 1.6 solar flare that on 5 August, and you can see the deabsorption curve. It was right over most of the United States. Next slide. And this is the solar X-ray flux for 13 to 15 August. The intensity of the X-ray classes are on the right-hand axis: Alpha, Bravo, Charlie, Mike, and X-ray. And things are nice and quiet. We're below about sea level. Next slide. This is the D region absorption for 15 August. The maximum intensity for the C flares were over the western Africa. And the absorption can be seen in the bar graph on the right. The vertical axis is the frequency, and the horizontal axis is the absorption in dB, where 3 dB would be losing half your power. Next slide. So let's see what a bad day looks like. This is a day where there's 1, 2, 3, 4, 5, 6 MRX flares. During each one of these flares, if this was directly overhead, you would have a radio blackout. And the radio blackout would start when the X-ray intensity passed into the M region, and would not be alleviated until it dropped down back to the high sea levels, as the axis shown on the right. So this would be a bad day. You would lose about, in the X 7.0, it looks like you would lose almost an hour of radio operation. Next slide. So this is what the deabsorption curve looked like for the X7. You can see that most all the United States was involved. The absorption curve can be seen on the right bar graph. Frequency vertical axis, horizontal axis is the loss or the absorption. And you can see the 1 over F squared curve of the bar graph. NOAA gets this out within a minute or two of a flare. So it's very useful. If you have the internet, you can immediately see what's going on. Next slide. So another interesting phenomena is called proton events. Next slide. So some flares, some solar flares will produce protons. As you know, protons are real particles. They have extreme energy. They arrive only 4 hours after the arrival of the X-rays, which means they're traveling very close to the speed of light. They have enormous energies because of their speed. When they encounter the Earth's geomagnetic field, they spiral about the field lines and dump into the polar regions. This results in what's called a polar cap absorption. On the left graph, you can see the almost, I guess, really about an M1 solar flare, and it produced in a very short amount of time a huge number of protons, as measured by the probably the GO satellite. So at the Earth. So it took only 4 hours for those protons to get to the Earth. The result is shown on the next slide. So as you can see, the polar regions have very high absorption numbers. But notice that if you're in the mid-latitudes, you can still communicate. You can talk across the United States, you can talk to Africa, you can talk to South America. You have good communications, and the proton event only affects your ability to go over the poles, like to the Soviet Union, to Greenland, some Northern European countries. You would not be able to get there because of the path over the polar regions. Just look at the attenuation on the right, enormous attenuation. Next slide. So now let's talk about coronal mass ejections and coronal holes. Next slide. As everyone knows, the Earth has a magnetic field. When the solar wind blows, which it does all the time, you actually see a shape shown on the right. Next slide. A coronal mass ejection is the ejection from a large solar flare of material from the sun. The sun, of course, is fully ionized, and the material from the sun carries with it the magnetic field of that material at that location. So it can either have a positive or a negative polarity with respect to the Earth's geomagnetic field. When a coronal mass ejection impacts the Earth's geomagnetic field, it produces a geomagnetic storm. And this either from the coronal mass ejection, or as I'll discuss in a few minutes, a coronal hole. This can depress the maximum usable frequency and increase deabsorption. Of course, this causes the Earth's geomagnetic field to ring. The planetary K indexes go up, and the F2 layer critical frequency drops because the heating of the F2 layer. The severity of the effects are a function of the polarity of this cloud of material from the sun, and we call that Bravo Zulu. If Bravo Zulu is south, the effects are much more severe. Next slide. So what I'm going to do is just simply show you the effects of a coronal mass ejection and a coronal hole with actual data. In 2011, we had the stereo satellite pair, which were in a Earth orbit, but about 90 degrees out with respect to the Earth, so that the stereo satellite cameras could see material headed towards the Earth. Next slide. We had a very serious beta gamma delta sunspot. It had all the characteristics of being a potential for a large flare. I'm sure the NASA told the astronauts to get inside. No excursions with the International Space Station, a dangerous radiation situation. Next slide. So this sunspot erupted, and you can see on the left at 0709 Zulu, the material cloud headed towards the Earth. It's continuing to expand at 0809. Next slide. Next slide.
Okay, I'll go back to situation. Okay.
Okay, and a couple of days later, that coronal mass ejection arrived at the Earth's ghost magnetometer. Shows a nice quiet day until about August, late on August the 5th, and the coronal mass ejection hits the Earth's geomagnetic field, causes a dramatic increase in geomagnetic ringing and activity, which can also be seen in the next slide. Here's the planetary K index going to 9. That's a serious impact. And it takes, each of those bars is 3 hours long. So it took many hours for things to settle down. Red is a geomagnetic storm. The yellow is minor storm activity, or actually called unsettled conditions, and then green is back to normal. So you can see how the planetary K index is affected. The Earth's geomagnetic field is ringing. The F2 layer is getting heated up. Next slide. So what's the effects of the impact of that coronal mass ejection? Left is a standard ionogram at 1300 Zulu, and you'll see that the critical frequency before impact was 5.9 megahertz. After impact, it dropped to 4.5 megahertz. Notice that there's fewer echoes, and so the signals are probably a little bit suppressed, besides the critical frequency dropping 24%. We were able to continue to operate Mars nets by simply moving down to a Mars frequency that was slightly below 4.5 megahertz. We had to deal with increased D-layer absorption, but we could actually operate if we knew that this is what was happening. So by having an ionoson, we could actually measure what the critical frequency was going to be, or was, and continue to operate our nets. Next slide. So similar to a coronal mass ejection, a coronal hole is a weakness in the sun's magnetic field that allow higher than normal wind speeds to leave the sun, with a very similar effect to a coronal mass ejection. This material, which of course is carrying a magnetic field, gets to the Earth. It interacts with the Earth's geomagnetic field, and depending upon where this material came from on the sun, it can have either a negative or positive Bravo Zulu effect. Next slide. So you can see the impact on the third panel. That's the GOES satellite magnetic indicator, and then the planetary K index can be seen on the bottom panel. Next slide. This is the wind speed got up to 700 kilometers per second, where 360 is normal. Next slide. So the effect was a 28% drop in critical frequency from 6.1, which was normal at 1300 Zulu, down to 4.4 megahertz after the high-speed solar wind event. The high-speed solar wind event, again, produces more attenuation, and we have to operate at a lower frequency. But as long as we know that, we can continue to maintain HF nets as we had always been able to do. So we can compensate for this by knowing what it's going to do to us. Next slide. So solar and geomagnetic indicator sources, 18 minutes past the hour on WWV, 2, 5, 10, and 15 megahertz. I don't think the 20 megahertz is working right now. You will get a synopsis of the solar and geomagnetic information, including the planetary K index and the solar flux index, and any warnings about solar storms. You can also go to the solar weather page on NOAA. I recommend using the Region 6 ArmyMars.org website, and you'll have information like you see below on our website, as well as the Austin, Eglin, and Boulder, Colorado critical frequency tables and other information pertinent to propagation. Next slide. Again, click on menu, select solar weather. You'll have those URLs as well as all the other printed information that would be of interest to you for solar weather. The Austin ionosphere is actually FTP'd directly to our website. We're the only ionosphere in the world to have that privilege, our only group in the world to have the privilege of an ionosphere sending the information directly to us. It actually FTPs to NOAA and to us. So even when NOAA goes down, the Austin ionosphere will continue to report critical frequency URL. It'll report the ionogram only when everybody else goes down. Next slide. Highly recommend solarhams.org, a very good site. Next slide. And finally, spaceweather.com. Well, this completes my presentation. Solar weather, next slide. Solar weather affects HF propagation. HF propagation is an important asset for contingency and backup communications for both the military and the civilian communities and emergency communications. Any questions?
Lou, I have a question that I've wondered about for some time. You mentioned, and it's well known that you have a 11-year cycle on the sunspots and the activity of the sun, and we're approaching maximum now. But of course, that cycle is actually a 22-year cycle,
right,
because the sun flips polarity at each, I believe they call it the Schwab cycle, the 11-year cycle.
Yes.
And so I've often wondered if there's any research, or of any effects on propagation, to whether you're on an even or odd cycle within that 22-year hail cycle.
I have personally been on the air for about 30 years, and I've never seen any real difference. What's important, of course, is the peak solar flux index. The higher it is, 20 or 30 years ago, we had better propagation. The critical frequency and the MUF stayed up later in the evening and functioned better, but I have not actually seen any. The last few solar cycles have had about the same peak solar flux index and sunspot numbers, and I have not seen any difference in propagation.
Okay.
That's just by, and I've not seen any papers discussing that really, but I think my personal experience would be that it doesn't make any difference. But there's just so much we don't understand about the sun, and that's why there's so many ionosons still functioning. We have to measure the data, just like I did in acoustics. You have to measure the parameters till you can actually get a model that works. And they really haven't figured all that out. Long range propagation prediction is still a difficult problem.
I have a question.
Yes, go ahead.
Is any of this data used for over the horizon radar?
Yes. Over the horizon radar basically uses the critical frequency, that MUF that we talked about, which is the critical frequency divided by the cosine of the takeoff angle. And by varying your transmit frequency, you can vary the impact point of your over the horizon radar. You can vary the range of the radar by simply changing your transmit frequency, which will change that maximum usable frequency angle and the impact. So you can scan across the ocean at different ranges by simply changing your transmit frequency. So you'll hear the American and the Russian over the horizon radar actually changing frequency, and they're going to be in Texas. They're operating pretty close to the critical frequencies that we use for our nets. So that's what they're doing. They're steering the beam and range by changing the frequency. Other questions?
This is Kai. Looks like very good information, but how does that impact the airline industry? Do they have to watch it constantly and find out?
I don't know much. I know the long range airlines used to use HF as a last resort, and they would certainly have to be careful to track it. And if they got near the polar regions, they're going to have all sorts of difficulties. But I would hope now that they have been able to go to satellite communications for long range emergencies. But it hadn't been. I worked a lot with the Navy P3s in the high Arctic all the way to the North Pole, and we had to use a local ionoson, a special type of ionoson called a swept ionoson, in order to get the best HF frequencies so that they can track do safety of flight of P3s flying from Thule, Greenland, all the way across the Greenland and across the high Arctic to study underwater ice propagation. So it was a real worry to be able to maintain HF communications across the high Arctic without actually measuring the critical frequency. Their models didn't work at all. And as soon as we put in a swept ionoson at Thule and started getting real critical frequency information, we started having excellent HF backup communications. And they really had nothing else in those days. This is back in the late 80s. Over. Go ahead.
Oh, that's good. I think the airline has been using the the North Pole route for a long time
Yes.
from Asia to US. So it looks like it may not be a big problem.
Yes, and it certainly could be, because there's very few polar orbiting satellites that have communications capability for the airlines. So I would be interested to know how they really do safety of flight. You know, that's an interesting problem.
Okay.
These layers run parallel to the ground, right? So the question is, if the ionosphere found in Austin a certain that height, can it be used, say, in Houston or Atlanta for the same thing for the same time, or there is anomalies in terms of the changing of the heights?
Well, you certainly, if you change latitude, as you go up in latitude from an ionosphere, if you moved the ionosphere north, you would find a lower critical frequency because the sun angle to the F2 layer would be a little lower, and there would be less ionization. But if you have, if you're at the same longitude as an ionosphere, you can move east or west by simply time delaying the response. Since the sun is moving from east to west, for example, when the Austin ionosphere fails, we can go to Eglin Air Force Base in the Florida Panhandle, and the longitude delay is about 45 minutes. So what happens over Eglin at about the same latitude as Austin is going to happen over Austin 45 minutes later. So you can make a very accurate longitude correction for locations that are of similar latitude. Going up in latitude is difficult, but you can do it by taking into account the change in the sun angle and therefore the level of ionization. So you can translate that information. It's more accurate to do it in longitude, but you can do it in latitude.
Thank you.
But the typical Austin ionosphere will give you good information out at 300 or 400 miles from around the ionosphere. So we have all of FEMA Region 6 plus covered with the Eglin, Austin, and Boulder, Colorado ionospheres. And then there are multiple other ionospheres on the East Coast at slightly higher latitudes. And then there's a couple of ionospheres in Alaska. And there's a couple of ionospheres in Antarctica. So they're everywhere.
Right. So, any other questions from the audience? So why do we have an S curve in during the night on the first few graphs that you saw? Lewis?
Yes. Say again.
There's some S-shaped curve that you showed earlier in the evening, and the daytime kind of go up, the nighttime kind of go for S.
Yes. It's just, again, as at nighttime the sun is not shining, so that the F2 layer is not being ionized, but the atmosphere is so thin at these altitudes that there's the recombination is not complete.
Okay. So
thank goodness. Otherwise, we wouldn't have any propagation at night. But what's interesting is the fact that we have to have a very, very thin atmosphere to get that high electron density at the F2 layer, and just that to be ionized, and at that altitude, recombination just doesn't occur very fast, and so that keeps that layer active.
right. Thank you.
This is Laura. Hello.
Hi, Laura.
I have a question again about an S curve that we saw on the night side versus day side. It was in the slide following the solar flares X-ray slide. It was really pronounced S. So I was wondering.
Oh, you're talking about the proton event?
Yes.
Yes, that's really what's your question about that?
It was very pronounced. So
Yes.
If you could comment on that.
Okay, well, the protons, it doesn't happen too often, maybe once every 4 or 5 flares. We've had a couple of flares in the last 6 weeks that had proton events. For some reason, and I think it's not well understood, the protons are ejected by the sun during a flare event. They're extremely dangerous for the astronauts. They would literally kill an astronaut because it's a real proton. It's accelerated at a velocity that would make CERN jealous because those protons are particles and they get to the Earth in 20 minutes, 20 minutes, you know, and so it's very, very high energy. They have a phenomena. They have ground-mounted proton detectors, radiation detectors, and they can occasionally actually detect the impact on the Earth of those protons. It's called a ground effect, but and I'm sure they had a ground effect with the one I showed at that very high intensity, but it doesn't take a very strong proton event in order to completely black out the Arctic and the Antarctic regions, because all the energy that hits the Earth is transferred by the Earth's geomagnetic field lines to the Arctic. So you might say the material is concentrated into the Arctic regions and not spread over the whole Earth where it had impacted. So it's a very interesting phenomena. What else could I answer?
That was it for that question. Thanks.
Okay, yeah.
Any other ham operators? I saw quite a few names here. Bob, you anything? Yeah, okay.
No, I thank you very much, Lou. I heard it again on twice this week or this month when I heard this story. It's an interesting story. Thank you.
Yep. Yeah, this presentation was enjoyed. I do this once a year for the amateur community. This kind of fills in all the parts of my very short solar weather update that I do at each club meeting, which is only about 10 minutes long. So I do this one once a year to kind of fill in all the gaps. And the Austin Astronomical Society, which I did last year, really enjoyed this. And they were sort of like y'all. They're knowledgeable, good engineers and scientists, but they really had little knowledge of radio propagation and solar weather. So they really, really enjoyed it. So it's an area that's I find fascinating.
Very, very good talk, Lou. We really appreciate you giving it to us.
I have a question. How does the tropo bounce at the TV stations, how does that compare to the ionosphere?
That's much, much lower and well below the D layer. And troposphere has changes in density and moisture that can cause bending of VHF and UHF radio waves. And I'm not a real expert in that, but you can certainly have that phenomena. And it's for example, when during Hurricane Harvey, we were able to talk from Katy, Texas to Austin to the Cape Mabry on 2 meters, 144 megahertz in the morning, because there was a layer of atmosphere, moisture, and temperature that allowed the 144 megahertz signals to bend a little bit in the troposphere. But that's all. So that's a different phenomena and doesn't involve the ionosphere. Unless you get a sporadic E layer where you might have a 50 or 100 megahertz sporadic E reflection. And then all bets are off, and you can be talking to people across the United States on 50 to 100 megahertz, but that's an unusual, poorly understood, not reliable path.
So it looks like all the space travel industry, you look at that, your solar weather before they shoot the vehicle up. So I will avoid those time or day or whatever.
Mm-hmm. Okay, well, if anyone has any additional questions, my contact information is there.
Yeah.
I encourage y'all that are hams to join the Austin Amateur Radio Club's Zoom meetings every the first Tuesday of each month at 7 p.m. And if you have any other questions, ask, and maybe some of you will be interested. We have classes scheduled for amateur radio licensing, and we actually have 2 very large scholarships available. And all that's required is that you live in Texas and have an amateur radio license. And we gave away $150,000 in scholarships on the Jim Greenwood Scholarship as of this month for the 2023-2024 year. And so I encourage anyone that knows children, grandchildren that needs scholarships. It's a scholarship that can be renewed with good GPA. There's no restrictions on where you have to go. You just have to live in Texas for the Jim Greenwood. I recommend austinhams.org website for more information on our scholarship program.
Yeah. So again, Lewis information will be in our website later on. So this will be recorded. We will place it on our website.
Okay. Thank you.
So thanks again for everybody, and it looks like a very good session. What good participation. So thank you, Clive, for inviting Lewis to talk to us. All right, thank you.
Thank
Have a
you.
good evening. Okay, bye. See you next month.
We see you guys. Just by the way, tag Technology Advisors Group is next Friday, week from Friday.
Okay. Yeah, on Friday.
See the website. We'll see you guys. Thanks.
Okay, all right. Okay, see you. Good night, everybody.